My name is Hakan Yılmazar, as mentioned already. I'm heading the application marketing for lighting. What does that mean? Basically, I'm responsible for the lighting business at Infineon. So also responsible for all customers globally and all products which can be used for lighting. And the focus is definitely LED lighting. So today I would like to talk to you about smart thermal protection, which can be achieved and provided by LED driver ICs. This is a kind of new way of thinking, which not only helps you to extend the lifetime of your LED system, but at the same time, this will also help you to reduce your cost in one or the other place. I will show you how in the next slides. So the presentation is structured. I will talk in the first section about the LED lifetime topics. In the second section, I'll go over to very simple basic thermal protection. In the following third section, I'll come to intermediate thermal protection with slope function. Fourth section will be about basically the highest and most advanced thermal protection, and I will summarize the whole ideas of this presentation at the end. And then there should be some time also for questions. So let's start with the LED lifetime. As you know that LEDs are brought very easily, very quickly in connection with energy efficiency. That's basically in all the medias. The mainly used word, this is true, and the efficiency is even increasing further. But nevertheless, if you make a comparison between the efficiency of LEDs compared to other light sources and the lifetimes, you will see that the lifetime is an even more convincing topic for LEDs, for the usage of LEDs. So here, I would like to show you the efficiencies of incandescent bulbs, basically, and LEDs. And you can see basically the efficiency of an incandescent bulb is, let's say, 4 times less or 5 times less compared to with an LED. And basically the CFL is also less efficient. But the difference between a T5 tube and LED tubes, basically there are no many factors in between. This is different if you look at the lifetime of LEDs. So an incandescent bulb has a lifetime of around 1,000 hours. A CFL can reach 5,000 to 10,000 hours, and an LED, basically retrofit lamp, is usually sold with 20,000, 25,000 hours. If you compare that lifetime with an incandescent bulb, you come to a factor 25. So that's what I mean. The lifetime is really much longer. And the LED bulb is not even the longest lifetime system. If you are talking about commercial systems, then 50,000 hours is required. And basically in higher value systems where it is hard to replace basically the light source or the related electronics, like street lighting, high bay lighting, the lifetime requirements goes to the direction of 70,000, 80,000 hours. And also in this space, street lighting, high bay lighting, lifetime warranties of 5 years and even more are quite often, actually. Having talked about this, LEDs usually have a very long lifetime. This is known. But what is also the case is that from a certain solder temperature and related junction temperature, the lifetime of the LEDs goes significantly down. And this happens in a quite small temperature range. I mean, the junction temperature, you see it in this diagram from, this is made for a Luxon LED, but could be also for another LED. The lifetime goes down from 120 degrees onwards, significantly down. And from 150 degrees Celsius onwards, the lifetime is going to 0 almost. So the curves might be different for different LEDs, but in principle, the message is that LEDs, despite the fact that they can have a very long lifetime, are quite sensitive from a certain temperature point onwards. This is not only valid for LEDs. There are, of course, everybody who is dealing with this matter, with the electronics, knows that ECAPs, electrolytic capacitors, are basically another very sensitive point in terms of lifetime. So in this curve, you see that basically even at lower temperatures, the lifetime of an electrolytic capacitor while drying out goes down significantly. But of course, the electrolytic caps are a little bit in a different position than LEDs. LEDs produce heat themselves, so they can't escape really. But the E-caps you can position a bit further away from the heat source so that it can be handled to a certain extent. But this doesn't change the general message that electrolytic caps dry out after a while and cause, in a lot of cases, basically end of life of the whole LED system. So in other words, or it's also the end of life of LEDs, as most of you know, it's not a sudden death, but light output, lumen output goes down gradually. So in other words, the electrolytic caps are very often basically the factor, lifetime limiting factor, as the LEDs in some cases as well. Now, why are we talking about heat so much? So LEDs are efficient, and efficient should mean usually that the power should be converted mainly into light output and not into heat. But if you look at this chart, you see that despite the fact that LEDs efficacies have been increased significantly in the last years, still a main portion is converted into heat. In this case, 60% is converted into heat and only 40% into light. Will that change significantly in the upcoming years? The answer is no. I mean, it might go up, the light output goes up to 45%, 48%, but there will be also in the future a significant portion will be converted into heat, basically. And just to give you an example that we are not talking about theoretical things here, this is a photo taken from a stadium in Guangzhou in southern China. And this picture has been taken basically 2 years after commissioning of the whole building. And you can see that there are lots of fails. In other words, here we can see a disaster, basically. This is not what an LED, especially a commercial LED system, should look like after 2 years. We can admit that southern China can be quite hot in summertime, but nevertheless, this should be taken into account while designing basically the LED lighting system. So what is industry practice? What we observe is there are driver ICs. Of course, before we come to the driver ICs, the easiest, simplest way is to use a heatsink, basically, which can be aluminum, ceramic, depending if it shall be electrically isolated material or not. There are also some plastics containing some metal recently, so different ways to do it, but I'll touch that a bit later. It always is very much cost related. Basically, there are some LED driver ICs in the market which claim to have thermal protection, and which is true, I guess, but this thermal protection is only related to the IC itself. As you can see in this chart, as I've shown before, the LED lifetime curve, or to say the LED lifetime goes down already much longer before then the thermal protection kicks in of the IC. So you cannot say that this thermal protection protects the LED lifetime or the lifetime of the electrolytic capacitors. This is just basically a protection for the very worst case to protect the IC. But then if the temperatures like 130, 140 degrees junction are reached, basically the LED lifetime has gone down significantly already. Another way to protect the lifetime of the LED system with ICs is to use an external NTC, basically a resistor with negative thermal coefficient. This can be done, but the impact will be that you have some additional cost, additional wiring, and also some additional space will be needed. So I will touch here in my presentation a way how you can eliminate such kind of NTC, basically. So as promised, showing you the cost roadmap of the Department of Energy. In this case, it's referring to an A19 replacement lamp, but you can also take another LED system. It will not look completely differently. The main message here is that in 2012, basically the LEDs made up to 40%, here in this case 39% of the cost of an LED product, in that case in an A19 lamp. And the thermal mechanical made up to 15% basically. But the situation is changing. If you look at 2020, you can see due to very strong price erosion of LEDs, the cost of LEDs, the share of the cost of LEDs of a lamp will be only 25%. And the heat sinks, basically thermal mechanical, will make up to 28%. So the absolute cost, as you can also see here, will go down, but this doesn't change the fact that thermal heat sinks will make up a significant portion also in the future. And what do I want to say here? Basically, if you carry overhead just for thermal peaks which are happening only very few times a year, this will be costly. If you can find a way where you can basically reduce your margin for these thermal peaks in a smart way, this will be basically rewarded by a higher profit margin. Let's come to basic thermal protection, to the second section of the presentation. What does that mean? So basically there are in the industry available low-cost LED driver ICs which just have a negative thermal coefficient, meaning the higher the temperature, the lower the current output. Here you can see in this slide the nominal current output at room temperature is 20 milliamps. If it gets colder, the current output goes up to 24 milliamps roughly, and if the temperature, when the temperature is going higher, the ambient temperature to the direction of 80 degrees Celsius, you can see that the current is reduced basically to 16 milliamps. If you take a resistor biasing, which is also quite often used, then the opposite will happen. At low temperatures, you will have lower current, only 15 milliamps, taking a nominal current 20 degrees Celsius at room temperature, and at higher temperature, you will have 25 milliamps in that case, basically. And of course, this can be still good enough, but in some cases, the resistor biasing, since it's an accelerating, self-accelerating process, the higher the temperature, the higher the current, the higher the current, the higher the temperature. So this dynamics is of course not shown here, but this can also have quite negative consequences on the lifetime of the LED system. So this basic inherent thermal protection, which is from this linear LED driver ICs, is quite nice feature. But there are some disadvantages related to that. I will come to that on the next page. So, but the advantages and disadvantages that will follow. So, coming to the advantages, the design is extremely simple. So, the linear LED driver ICs can just replace a resistor, and maybe just another resistor needs to be added to adjust the current, but that's about it. It's quite low cost, of course, not as low cost as resistors, but still we're talking about a very low cost solution here. And in a lot of cases, the protection, let's say the thermal, negative thermal coefficient, basic thermal protection can be sufficient, because here in these systems we are talking about a high number of low or mid power LEDs, which are usually spread around the PCB, and this can be sufficient to protect the lifetime of the LEDs. Now the challenges, it's quite obvious the light output is reduced even before reaching a critical state. That's actually undesired usually. We can say it's not significantly reduced, but there's a slope up to, let's say, 40, 50 degrees Celsius or even 60, There's nothing critical about the lifetime of the LEDs, but still the current is reduced, and here with the light output is reduced. And also vice versa, if the temperature goes below into minus, below zero, then the light output is increased compared to nominal output. This is actually not desired usually. And in some cases, the reduction of the current might not be sufficient. Think about under cabinet lights. I mentioned that LEDs are usually spread, but sometimes the customers want to put the LEDs quite closely to each other to get more higher light density, basically, higher light output. In that case, it might be critical, even if you're using low power or mid power LEDs. And sometimes there is no opportunity to dissipate the heat. If you implement such kind of light strips into furniture or other things where they cannot dissipate the heat, or in luminaire, narrow luminaire, then it might be still critical. So the slope you cannot not adjust really. Let's come to the third section, intermediate thermal protection with slope, which is addressing already some of the topics which we've seen in the basic thermal protection. So this thermal protection with a slope curve has been implemented at DC-DC buck LED driver ICs. Here we are dealing usually with high power LEDs, meaning 350 milliamp drive current and above. And here you can see also at the curve already that the problem which we have seen and discussed just before is addressed. There is no negative thermal coefficient until a certain temperature point where it gets critical. Here the junction temperature is shown of the IC, and basically the slope, with the slope function, the current is reduced. This is desired, I think. And here we are talking about real protection, not only of the IC, but of a protection of the LED system, as you can see here. I've taken the same curve, which I've shown before, related to the LED lifetime curve. And here you can see that basically the current is reduced just when it's required. So not before the critical stage is reached, there the light output will remain constant because the current remains constant. And when it's coming to the critical stage for the LED lifetime, the current is basically reduced. And these LED driver ICs are also, as I mentioned before, you don't need to use any external NTC. If you can thermally couple these LED driver ICs with the LEDs, which is usually the case for DC-DC buck LED driver ICs, they're used usually on the light engine where the LEDs are available, then it's a quite good solution. Let's still discuss the advantages and disadvantages. So as mentioned, you can protect the lifetime not only of the IC of the LED products, it's also very easy to implement. We are talking about classical DC-DC buck LED driver ICs, just with a few components around it. And the cost is also quite low. So also you can, since you can avoid an external NTC. There are two challenges identified. Basically, the reduced LED current can cause color shift because we are dimming in an analog way. And some LEDs, they're getting better towards a color shift with analog dimming, but there can be still some color shift. Second point is that the over temperature protection here in this intermediate thermal protection cannot be adjusted. And in this case, basically, the customer doesn't have the flexibility if they want to drive the LEDs harder or basically increase the lifetime, let the thermal protection kick in even earlier. So this is a fix in the intermediate thermal protection. Let's come to the advanced thermal protection. Here we are talking about a new generation of LED driver ICs for 60 volt, up to 60 volt breakdown voltage. The same is valid for these LED driver ICs as mentioned before. They can be used as a thermal sensor, so no NTC required. if they can be thermally coupled to the LEDs. And also there's a slope function which protect not only the IC but also the LED system. But in addition, there are a few more points which I would like to present to you. One is an adjustable trigger point. Another one is PWM output, which keeps the light color constant. And in addition to the fact that an NTC is not required, the flexibility is still kept to use an external NTC. First point, adjusting the trigger point. Why is that important? As you can see here in the curve below, you have the flexibility with these devices to adjust the trigger point. Some customers might not be even interested in the thermal protection. They want to drive the LEDs hard in terms of lumen per dollar because they want to get as much light output as possible from the LED system. Then they can take a resistor value which ensures that the thermal protection doesn't kick in so early. The other way around, when customers are interested to have a very long-living LED system, they have the choice to adjust the trigger point at an earlier point. And this can be done very easily, very simply with an external resistor value. So we have an application note where it's described which trigger point, and you can also see it in this chart, which resistor to select in order to adjust the trigger point. Now, let's come a little bit away from the technical topics, but to come a little bit to the human aspect. What do we perceive? I chose to share with you this SSL dimming curve for the NEMA SSL 6. This is done for dimmers, but the principle I think helps a lot to understand how the human eye reacts to light output, what we perceive. And as you can see, at higher light output, the dimmers can go faster because the human eye response is exponential, meaning at this stage, the human eye hardly recognizes a light output change, light intensity change. And when it comes to the lower light output ranges, the human eye can detect much more. And the more down you go, the more the human eye sensitivity increases. So I'm telling it to one purpose, but please be patient for the next slide. Why am I telling you this all? We mentioned already that the human eye is not so sensitive at high light output levels and getting more sensitive at lower light output levels. The second point is the human eye is quite sensitive towards color temperature changes. This one also when the sensitivity or the light output, light intensity is lower, the sensitivity is also towards this higher. But in general, compared to the light output, light level output, the light color is much better perceived by the human eye. And what I'm showing you here on this left-hand side is basically changing the current output level of this new LED driver ICs, ILD 6000 family, and you can see here on the x-axis the nanometer, the wavelength of the light, and here the light output at these wavelengths, and you can see basically the wavelength range remains absolutely the same when you dim down with this PWM methodology, and that means there's no change in light color, meaning where the eye is sensitive, basically there's no change. And this is just again a chart to show at which colors, at which wavelengths the eye is sensitive. The reason why I'm telling you this is what we measured also in our laboratory is with these ILD 6000 products, when you heat up basically, or the LEDs heat up the system, the current is reduced, and then at a certain point there's a thermal equilibrium reached, and the current doesn't even go down too much. So, and the light color doesn't change. What happens is, I mentioned at the beginning of my beginning part of my presentation, if we have only a few thermal peaks in the year, during the year, the very likely case is that the end user will not even recognize when with this, if you use these LED driver ICs, that they're in thermal protection mode, because they are reducing the current slightly smoothly in a slope mode, which then again reduces the thermal load. At the same time, the light color is not changed, meaning basically the end user will not see anything much. It's of course not undesired, if it's not desired that it happens 5 times or 10 times a day, every day, then there is something wrong with the design. But if it happens only a few times a year or seldomly, then this will not be perceivable for the end user. Now, what is advanced? One further point is we always said the LED driver, you may not use an NTC if you can thermally couple the LED driver IC with the LEDs. But what happens if you cannot? Because in some cases, these DC-DC LED driver ICs are implemented in the LED driver, which is further away from the LED light engine. So in those cases, you need an NTC or PTC, and in those cases, for those cases, this ILD6000 family allows the flexibility to use the NTC as well. You don't have to if you can thermally couple, and you can save costs. But with the same IC you can still use, you don't need to change it to another one when you cannot thermally couple basically the product. So I would like to summarize my presentation. So one of the key selling points of the LED products are their lifetime, not only the energy efficiency, which I've shown in one of my first slides, because here LED products are factors above other light sources. Nevertheless, this LED lifetime is not granted or given for free. If the temperature with which these LEDs are operated is high, then either the electrolytic caps can fail or the LEDs themselves. That means that thermal protection is essential for LED lighting applications. As I've shared with you, a large part of the energy put into the LED systems, more than 50% goes into heat. And basically implementation of a slope curve of over-thermal protection ensures not only the lifetime of the LED driver IC, but also in addition the lifetime extension of the LED system. If you can use the LED driver IC as a thermal sensor, if you don't need to use an NTC, this reduces not only your cost, also your design effort, and also helps to save some space on your PCB. Last but not least, coming to the smart thermal management of the new ILD6000 family. In addition to the slope and using the IC as a thermal sensor, you can adjust the trigger point of your thermal protection, which allows you to optimize between lumen per dollar or longer lifetime, very high quality, long living systems. The light color will remain unchanged during thermal protection mode. And also you still have this flexibility to use an external NTC for the cases where you cannot thermally couple the LED driver IC with the light engine. So just to round up my presentation, you can find a lot of material in the Infineon website. We have a product side for LED driver ICs or fluorescent ballast controllers, but in addition also we have an application side where you can find also the required documents.